Today I want to change how types are represented. Currently, the type is just an enum that tells us whether that's a struct or an enum or something. I want to change that so that it just says what type is it as a string. And that might seem crazy, and the string is supposed to be something like, like a struct with x, which is an int, or y, which is an int, something like that. That might seem crazy. We are losing a lot of the type safety and the benefits of this doesn't even. How can we work with strings and do type substitution and whatever in that representation? But I think there are two big benefits of this design versus the current one. The first one is that this representation with enums is inefficient. A string is a slice of bytes, which means it has a pointer to bytes and it has the length of that. The egg type here is a map, which is what is sliced to some map buckets, which is 16 bytes plus the amount of items in the map. So map is 24 bytes. And we also store an enum tag that's 25 bytes. That means the individual map entries here, which contain a string and an egg type. Each of these has 16 bytes plus another 25 bytes. That's 41 bytes. And the map doesn't just store a single one of these, it stores a couple of map buckets rounded up to a power of 2. So for example, for this dynamic type in here, that has 1, 2, 3, 4, 5, 6, 7 entries. We actually store at least 8 times 42 bytes. That's 300 something bytes. If we look at this encoding here, just the source code here is 200 bytes. If we would just store that as source code versus a structured representation, that's more memory efficient. And that these 300 something bytes, they don't even contain the individual strings themselves. These are just the pointers to the strings. So obviously there's a reason that we don't store the entire program as a giant string, but that we pass that into a tree because we want to use that structure of the program. We want to traverse that and iterate over the expressions and stuff like that. But for types, that we actually don't want to do that most of the time. When you have this egg type that maybe contains a struct, when we want to figure out the types of the fields, we can't just switch on the egg type and look at the struct, because these types may not be self-contained. Because the types may say, oh, I'm actually a recursive type. Please look 3 levels up in the type tree, basically, to find out what type I'm actually. So whenever we switch on a type, whenever we want to traverse into a type, what we actually have to do is something a bit crazy. Let's show that. Yeah, we have to do this. Extend one level is what we have to call on that. We know that this, for example, compiles a switch. We know that's an enum. But before we can use that enum variant, the types of the variants, we have to call extend one level, so that the recursive types at the bottom that refer to the root node, that they are replaced with versions that, that we want to grow the type at the bottom as we traverse down into that at the top. And we do that everywhere. That this extend one level is extend one level. That is in a lot of places. Which means we don't really treat types as this data structure that you can traverse into, but instead as one unit. And whenever you want to do something with that, whenever you want to do an operation on a type, you actually have to call this extend one level function that gives you a map of new types, basically. And having that structure here is actually more of a foot gun, you know. It makes it easy to create invalid types, or types that are no longer like canonicalized, or types that are, you know, kind of bad types. Speaking of, in a lot of places we canonicalize types, which means we simplify types to the minimal version. And we don't really do that consistently. Or at least we do that, I think we do that in a lot more places than we actually need. And we do that because, well, in some places, you know, if the type is too complex, things don't work out. Basically, this impacts correctness. If we have one type that, like two types with different representations that actually represent the same values, the same type, just one is written a bit more inefficient than the other. And we can even look at an example of that in the type in here. You know, these two types here, they are the same type. This is an enum of either A or B, and if it's B, then it's recursive, like one level up. So the B variant contains another enum, A or B, which then the B variant of that contains another enum, and so on. That's equivalent to this type. So when canonicalizing, we kind of boil down types into their minimal version. And if we would represent types as strings, and rather than constructing types by creating, you know, new egg types, like eggtype.array of some other type, if we would rather just say we have functions for creating types, and we have functions for traversing down into types, and internally how the type is represented, you can't even look at that, you know, whether that's a string or a tree or something else. But at these kind of boundaries where we construct new types and where we inspect types, those boundaries we control in a way that types are always canonicalized. Then we can remove a lot of these defensive canonicalization calls in the code. So that's the plan for today. Or like, not today maybe, but just getting started with this. We place egg types by a string. Yeah, I think that doesn't really fit into this egg module. So let's actually create a separate folder for that, so that we can have types as a separate thing. Hang on, where's the egg? Here. We want to move that into here. And then we call that mod, because that's the main module file, and then create a separate file for the type. Like so. Yeah. Ooh. And then this will contain the definition of types, but also the functions for working with types, for traversing down into them, etc. Currently that's kind of a bit all over the place. I think there's like a type algorithms or types, yeah, these kind of functions. I think some of these would have to be in the types module directly. Yeah, so let's just look at types at this type and create a new version that is just a string. That's memory efficient, and it doesn't provide this false sense of security in the API. And instead of these, we just have constants for the never type. So I think we actually have those already. Somewhere, I think in here, yeah. Type never is egg-type.never, and so on. And we want to have similar functions, but they instead create strings, but also canonicalize types automatically. right. So how do I want to represent types? I think types should always, like I want a very uniform representation in the string. Basically, I want to represent this. Struct and enum lambda. All right. basically are these functions that automatically canonicalize types. And then have a separate function for traversing down into a type. Maybe some kind. And that then contains the actual type. Like basically the enum that we had before. Well, let's maybe get that. Oh, I see. And this doesn't exist. Yes. I could maybe split that into two phases, maybe. First, make it so that the egg type automatically canonicalizes stuff and has this internal type representation that you can't look at, but it's still basically the current egg types, so all the algorithms don't change. And then, as a second step, replace that with a string. Maybe. I'm not quite sure. Maybe some sort of internal kind. That is more like the existing. Enum, including the recursive type. I think I like that. Cutting off the array and the closing parenthesis, leaving us with only the inner type. That's pretty cool. Basically, I'm writing a small parser here, I believe. Which is fine by me, you know. here we just need to count the number of opening parentheses, I think. Mm-hmm. don't make things more general than they need to be. I think it's way easier to have these as concrete types specified in here than a general primitive type that has possibly multiple arguments and so on. We don't even use that. So oh, we could put like a marker type in there, something like this. That's the benefit of, you know, rather than recursive of -1. That's the benefit of being less strict about types. Yeah, I think that's pretty much it. I mean, I'll have to extend recursive types. But in general, yeah. Root. I like that. is really supposed to return the kind. Not sure that's what we want actually. I'm not sure at all. Like if we have some type like I think this needs to be canonicalized afterwards. Okay. This is probably fine. this will actually use a string builder or something like that. To make it more efficient. And I mean, this is way more efficient than creating lists and hash maps and whatever all over the place. So, a string builder. No need for a new map. No, just concatenate to that string and we're done. That's simple. That is pretty cool. Hell yeah. Hmm. Hang on, is that correct? I'm not sure. Oh yeah, because this root is always in... It's never deep inside the extension, it's always in the top level. Still, weird. Mm-hmm. Right, and that is basically this one, this file, translated to the new architecture. Yeah, this is no longer really a thing. Mm-hmm. Nice. You know what, let's play around with that. Let's say let's actually create a new file here. Oh wait, maybe not. Maybe not. Maybe let's just, you know, Yeah, true. I see. Yeah, this one. Nope. Not having that. True. The builder. Hmm. The aunt. Interesting. Could have sworn there were keys. Alright. Sure. Let's do like an ad hoc implementation of that. Fair. Ooh. I see. Well, Hmm. Mm-hmm. Hmm. Let me see. So we have A and B. A is an int, B is this struct with C, which is an int, and D, which is recursive to this surrounding struct. Then when we navigate into that, we get the struct with A being an int, and B being this right here. A struct with C and D, where D is A and B with the recursive type. That's perfect. That is perfect. Okay. We have an efficient representation of types that you cannot accidentally switch on. We have to call kind on a type, and that returns you this sort of thing. Like for example, this is a struct, and then the fields have self-contained types again. That's pretty amazing. Then, what's the next step? I mean, we basically implemented this extend one level. So let's remove this one. I mean, another would be the builder is kind of unnecessary. Well, not really unnecessary, you know, but I should probably migrate these over to the other file. But the more important part is canonicalization. I think I'll move that into the type file. And hang on, builder. Nope. this will not contain all the type algorithms and stuff, but it will contain the canonicalization and the walking down into types. It doesn't need like matching or unioning types or something. That's like those type algorithms are still part of the compilation stage here. But just traversing types, that will be here as well. Yeah, types are always self-contained, I would say. Crazy that a lot of this code just becomes simpler by representing types as strings. That feels wrong, you know? Boom, done. What? That's crazy. This might also be nice. Yeah, bubbling up a recursion at an index. We don't need to like traverse the tree and kind of keep track with how many recursions have we seen and kind of have this reference to a mutable counter and stuff. We can just walk the string from like the front to the back and count the ticks that we've seen. And if we are at the tick with the index, then we can just look back for an opening parentheses and look at the front for a closing parentheses and kind of just replace that part of the string with something else. How are all these algorithms getting simpler by representing types as strings? What? That feels wrong, right? You have these nice fancy trees that you traverse, and then, you know what, let's build types as strings, and boom. What? I think it's easier because you can kind of ignore the tree structure where you don't need it. But because the string still has a quite regular form with parentheses and so on, you can, kind of in the place where you want to have structure, you can very easily kind of retrieve that structure back out of the string. That is nice. Also weird. Man, what? That's crazy. And we don't even need to build like this. Allocates all over the place. This creates hash maps and whatnot. We look for this. We look for the tick. We look for an opening parentheses back a bit further back. We look for the corresponding closing parentheses, and then we just concatenate 3 strings or something. This has no right to be so elegant. That's crazy. This is really like mind blown. What? That's... I can't get over that, honestly. How is representing types as strings both more memory efficient? Easier to implement correctly, and designing a better API around that. Plus the algorithms get simpler. I was skeptical of that idea first. I was like, that seems weird, replacing types with strings. But then I was like, I guess I could try it, because I don't really use the structure of the types. And then even for the algorithms where I use the structure, I want to ignore the structure most of the time. That is crazy. Okay, I mean, I'm not complaining, What? That's just crazy. Okay, so we're looping over the type. So if type.type.chars, I think that's, here we also need to do that, chars. Get the char the cursor, if that is this one. Yeah, so we have a count, which is initially 0. And the outermost part cannot be a recursion. Yeah. This would point to the, the tick. The cursor is the tick. Then cursor -1 would be the opening parentheses before the tick. and this is the place before that. If that's the closing one, then we increment the nesting. If this is an opening one, then we decrement the nesting. Well, I guess first, if the nesting is 0, then we just break. That's crazy. Mm-hmm. Mm-hmm. Oh, I could just do that. Oh, that's nice. That's nice. Let's just call it closing. That's crazy. That's honestly crazy. Yeah, an opening one increments the nesting, and a closing one. Well, if the nesting is 0, then we break. Otherwise, we'll just decrement the nesting. Then we move to the right. Makes sense. Alright. Now, cursor, and that's actually, what's that, like a tick? I mean, I could just find the opening and closing parentheses of the recursive type itself, and then of the parent type. I think that makes sense. Because there's no nesting within that, so. Man. That's cool. That is straightforward code, honestly. Much simpler than this one. Crazy. That's cool. That is so cool. yeah, this will not insert any new lines. It will basically just, you know, strings can have a new line and then everything until this single quote gets skipped. So what? That is crazy. That is honestly crazy. What? Let's simplify that a bit. What? That is so much, like, even the number of lines. This is like what? Oh, I can't see that right now. Let's see. Does it tell me the number of lines? Nope. Okay, but 450 from like 300, oh no, here, from 60 lines. Alright. And then we have this one from 450 to, oh, and also this needs is recursion. So to here. The new one is so much shorter. That's crazy. Man. Yeah. Is self-contained? That's actually important, yeah. Man. That is... Man. Wow. I'm honestly amazed. That is super cool. Alright, so this doesn't need to be some, you know, function. Nope. Is the new one simpler? Maybe. I honestly don't know. Honestly don't. I think I just want to keep track of the nesting. It's gonna be simpler, isn't it? Because we don't need to care about never or int or byte or struct or whatever. We just count the number of opening parentheses. And whenever we see a tick, we pass the number after that and see that the nesting matches. How is a string a better representation for working with types instead of a tree? That's feels illegal. All right. Man, no. Crazy. What do I want to do? So if the char is, you know, an opening parentheses, and nesting is nesting plus one. Yeah. If it's closing one, then we decrement the nesting. And finally, if the char is that, then we just pass the number afterwards. And that would be, let's see. Okay, we do need a cursor. And we could possibly loop. Oh, that just checks the nesting, I see. You know, for the internal kind, we do need to pass that number somehow, don't we? Oh, then we know that this is the entire type. I see. I see. I think we can do consume name because that looks for alphanumeric ones. That's crazy. So we have. Oh. Yeah, I don't know. Let's do that. This is not allowed. How's that? How's that shorter than this one? That's... That's crazy. That is honestly crazy. That's... That is indeed crazy. Okay, does the nesting make sense? Let's see. So if the level is 0, okay, I think nesting, let's say we only have a recursive type with 1. That should be invalid. The level is 1, the nesting is also 1. Alright, because the recursive type itself also counts as nesting at that point. So we really need to check that. Yeah. Just making sure that there are no off-by-1 errors. I mean... This is so elegant. It feels hacky and weird, but I love it. Alright. Alright. Yeah. Then this calls is equivalent. And then a list of types that we are currently comparing. Given 2 types, are they equivalent? Well, we don't need to do that. Don't need to do that. We can just call is equivalent logic. I see, because then we can use returns in there. Kind of weird, but sure. Sure. yeah, here we switch on kind, and this automatically extends the type at the bottom. It takes care of everything. So here we check that. Oh, kind variable, not variable, like that. No. Yeah. What else do we have? We have let's see. Yeah, we have never byte int type array. Never byte int type array. I can remember that. Never byte int type and array. Just so I don't have to do this all the time. Yeah. Then B has to be an array or return false. Yeah, we just need to check this one is equivalent for the A item and the B item. Like that. Simple. We can even inline that. Shorter than the generic primitive bullshit from before. Yeah. Here we know that B is a struct, otherwise we return false. Fields must have the same size. Alright, and then we have the A type, that's A field of value, and the B type is B field, so get maybe that key, or we return false. Boom, boom, perfect. Perfect. For enums, similar. For lambdas, we check that B is a lambda, that the arguments have the same length, that zipping them, that they are all equivalent. Yeah, and then the return types, which are no longer references, are equivalent. Amazing, and this, no need for that, because the types are definitely extended at the bottom. That's pretty cool. I have to say, that's quite amazing. Ooh. 3, 6, 8 in here, canonicalize. Alright, yeah, we don't need that. Now just do bubble up recursion number I, please. And if that is self-contained, amazing. Also, I don't like this operator. I kind of like that when, you know, sometimes I needed to check for exact equality, sometimes I needed to check for whether they are actually equivalent. But now that types are canonicalized by default, I think we should just have a function is equivalent, and, well, you know, then in here we use is equivalent. Yeah, plus the equality is super efficient now, because it's just a string compare. And that is implemented as memcompare, which is implemented in bytecode, aka basically assembly, and that is JIT compiled to machine code later on. So this is really, really efficient. It's so much more efficient than before, where we kind of walked trees and looked at hash maps, and oh my god, even comparing two hash maps is quite a challenge, right? We need to compute the hash of several strings, and then I don't know what I mean, yeah, this makes sense in here. No. I mean, yeah, that too, but yeah. Now we can just check if the types are the same. Hashing that is just hashing the string. Oh, that's so cool. Now, why is it so complicated? A dot type, which is a string, is B dot type. Boom. Oh, hashing is just type dot hash. Oh, sorry, type dot hash. Don't want to get into infinite recursion then. I mean, come on. That's cool. That is really cool. Yeah, okay. Compiles. Yeah, canonicalizing types. Now that should do something, at least. Which means in the main file here, yeah, when you wrap that, you kind of let's say we want to create a type struct with a map where C is an int and D is foo. Let's print that. Oh no. This is self-contained. Oh yeah, right, we do need to break at some point. We could just immediately return true, I guess. Oh, hang on, what's going on there? Oh, yes. Yes. Okay, we do have, like, this is super cool. We have a type with A and B, and then inside that is a struct with C and D, and that is recursive, so that D then again contains A or B. But when we wrap that in C or D, that automatically gets canonicalized to C or D with then, you know, A or B, which is again recursive to this type. Oh, that is nice. That is just nice. That's super cool. Okay, yeah, so change types to strings, and it's apparently way more, you know, way more ergonomic than before, and more type safe in some ways at least. Like automatic canonicalization is really nice. You're not tempted to switch on the type. This is the coolest refactoring, like one of the coolest refactorings I've done, I believe. Switching from a typed tree representation to string and making that more type safe and faster and safer and simpler. Who would have thought? Well, okay, yeah, next would be integrating that into the rest of the compiler, like kind of, you know, enabling that and then updating the places where we use egg types to no longer canonicalize them, because we do that automatically, to, you know, do some bookkeeping, removing the extend type, adjusting the switches. But it's quite late, so not today, some other place. Alright, see you then. Alright, let's integrate these new types in the rest of the compiler. So I think let's just uncomment that and maybe comment that out and try to compile that and see where it fails. Yeah. So in toast to egg and types compile, yeah. Alright, yeah, compiling toast types to egg types, that's bound to be weird. Alright, so we have some primitive type. But that's still, those are still toast types. Toast types, still toast types. Egg type dev. Here things become interesting. Not difficult, interesting. Alright, so for primitive types we compile these. That actually seems reasonable, I think. Yeah, usually the order is a bit different, but I mean, who cares, right? Yeah, for variables, I think this is an egg type. Type var. Let's actually call that type variable, I think, to make that consistent. So in here, do that, and then here we can do that. Yeah, this is, you know, recursive types we just create. Yeah, let's, you know, let's create recursive types. And parentheses around that, that's important. Yeah. Alright. this would be type struct. Nice. Without canonicalization. No, without canonicalizing. Like in general, I think that the way compilation works is we do create incomplete types here. For example, this recursive type. So we don't want to do any sort of canonicalization, but after compiling an entire type, we then want to canonicalize that. Yeah, this doesn't canonicalize anyways, this one does, so this has to be without canonicalization. Let's see, without canonicalizing, sure. Let's look at the array type, which is there, without canonicalizing, boom, and this just calls the type array without canonicalizing the item type dot canonicalize. Nice. Yeah, type variable, type recursive, which is guaranteed to not be canonicalized. Then here type struct without canonicalizing. This would be type enum without canonicalizing. Type lambda. And I think this just takes the arguments and the return type. Not entirely sure, but that would make sense. Alright, then here we have primitive. Oh, but that's like toast types, has nothing to do with egg types. Alright. So we prefix calls with the module, we solve imports, whatever. Then here we compile them. Down here. Yeah, and let's do canonicalize once down there. Alright. Yeah, compiling types. Yeah, this is weird that it's so similar. Also take types and defs, which are egg type defs. And this one takes toast type defs and stuff like that. Not sure how to feel about that, but okay. This would be type array without canonicalizing. Alright, so we have that. And let's actually stop with that. Let's say we only want to compile to the egg, and that's it. So that would mean in here we kind of disable that part of the compilation pipeline. Oops. Not what I wanted to do, but sure. Okay, that exists 2 times. Well, that's unfortunate. Indeed. Yeah, no, this is not nonsense. This is nonsense. as is this, as are probably some of these. Well, we'll see. Switch type.value in the egg.mod. Where's that? Up here. Writing egg types in an indented way. Ooh. Well, yes, that is kind of difficult. Let's say, and this is the internal kind, I think, because we don't want to extend types at the bottom. And then here we have variable. Yeah, and we need to handle the recursive one, that makes sense. 175 primitive is not a thing, that's true. Instead we have separate, like byte and int and never, and type and array. Oh, I think that should actually be well, I think we'll need to do something like in here. Like if this is a single line thing, single line is field.value.format. And if there's enough space for that, so if indentation amount times 2 plus array space dot len plus single line dot len, if that is less than the limit, then we'll just print array and then the single line, otherwise we're going to have to do a multi-line part, and that's going to be, let's see, an array, then new line, and then the indentation plus 1, and then the item. Like so. And this is just item.font. Alright, dot star is not a field on egg type. True. Don't need that in here. Hang on. Oh, here. Sure. Yeah, the matching, that's bound to be different. check coherency. We union an existing type and a concrete one. Otherwise, we just take the concrete one. Yeah, that doesn't need to be canonicalized, I believe. And in here, we don't need to do that. Clean. Yeah, if the concrete internal kind is never, then we just return true. Otherwise, we switch on the generic kind and that can either be a variable . Let's do that there, and then here we can just check. Concrete is never, boom, generic, clean. Although this is, yeah. I don't know. Yeah, this has to be a byte, or we return false. We can just say that has to be a byte. Boom. Oh. Same for ins, same for never, same for type, same for array. Well, array is actually a bit. Here we have the generic item, and the concrete item is concrete.array, or we return false, and then the concrete item match against generic item. All right. True. Then for struct, we do that, makes sense. For enum, we do that, makes sense. For lambda, we do something, and here we don't need to care about that one. Here we don't need to check with the return types. All right. I like that. Cool. Quite nice. Yeah. Yeah, here we do need to we need to go with the internal kind here. Because we don't want to traverse infinitely down into types. So if this is a variable, then we get the substitution. If this is a byte, then there is nothing to specialize. We just return the type. Same for the int, same for never, same for type. For arrays, well, we have to specialize the item. Yeah, I think we want to replace all the occurrences, and then afterwards we want to canonicalize that once. That makes sense. So I think let's have some sort of specialized function that can specialize types. And it will also canonicalize them. So this will do type.specialize rec using those substitutions. And then we'll canonicalize them, like so. Yeah. Yeah. No longer need that. All that. And this is a struct. Right. Yeah, and this one specializes the individual entries. That makes sense. Ooh. Oh, no. Yeah. True. Then 409 is down here. Collect vars. This can probably be even more efficient. Or just iterating over the string and doing stuff like that, but yeah. We just switch on the entire kind. All right. And then in compile fun. Nice. Yeah, I think all the canonicalize stuff. I'm just gonna go through this and adjust things as needed. So when we compile types, they are canonicalized. We don't need to do that separately. Same here, we compile a type, it's already canonicalized. That is clean. Then, I mean, yeah, we have a couple of operations. They just refer to type int, type string, type, compiles the type, yeah, this is automatically canonicalized. Very nice. Same here, type enum automatically canonicalizes stuff. Yeah, we don't need to extend types one level. That's cool. Condition. All right. The result of unioning things is already canonicalized. All right. Type lambda automatically canonicalizes stuff. So no need for that. Oh, no, that doesn't fit there. need to extend types. We can just say kind has to be a struct. I think that's pretty cool. Like in the general, function code, we don't even need to think about canonicalization or compiling, extending types when traversing down into them, stuff like that. Where do we get the lambda type? I mean, why the indirection? Oh, I see. That's why. Yeah, okay. Cool. I see. Okay, so the types that we are inspecting, we kind of traverse down into them using the kind, so they get extended at the bottom. But we don't want to we don't want to automatically canonicalize the return type. Mm-hmm. And yeah, internal is the kind. Oh, hang on. This is the join logic. And join is called up here. That type then has to be canonicalized. Yeah. And it would be a bit more efficient to just say internal kind here, because we don't really use the values of those fields. And then in here we do kind, so you know. To extend it at the bottom, so I think that's fine. Yeah, look up. Let's see. Match against. So we have arguments, we have parameters, and these are fun args. I see. Then the builder of types. Some of these are quite weird. Let's just copy them over to the type module instead, and have them here. And these are just built-in types. Type variable, never byte, int type, array, struct, enum, and lambda. Undo stuff. I removed something here. The builder. Sure. Because some of those types are actually useful. So type var t. Not sure about that. Let's not do that. Type nothing. Yeah. Yes, please. Type struct, which is a map of bytes. Type bool is an enum of true and false. Yeah. Type ordering is an enum of less, equal, or greater. Type info is an enum of this. Oh, this is recursive here, let's see. Okay, so I think in order to make that work, I need to do it without canonicalizing up here. And just construct that without any form of canonicalization. Like so. Because I'm like explicitly constructing recursive types here. And then at the end, I say canonicalize. Makes sense. But let's be even better. Let's say canonicalize of this thing to make that a bit more obvious up front. That even though they are not canonicalized, we do that afterwards. Alright, plus these have to kind of change as well. Let's make that like this. Nice. Yeah, I like that. Then type info field. These become much easier now. Because this is just type info dot kind dot kind dot enum. That's an enum, and then we access the struct field. Like that. Dot kind. Oh, no, that's an enum, and then we get the struct variant out of that. And then we access the array item of that. Nice. Yeah, the fields. Oh, that's actually even easier. It's just this one. And then a single field would be type info fields. Dot kind array dot unwrap. Nice. Now, variants, let's build that up similarly. So that would be kind enum.unwrap get enum. And a single variant would be type info variants dot kind dot array unwrap. Lambda is, well, that type info kind dot dot, yeah, that's an enum, and then lambda. Boom. And then this is type info lambda that is guaranteed to be a struct. And then we can do fields, something like that. Hang on, abstract. That's a list of fields, and then we can do args or arguments. I'm actually not sure. Arguments, yeah. Oh, that's cool. Nice. Oh yeah, and then type with field and fields. It's going to be similar to that up there. Hang on, you know what? Let's even add better accesses for types. Let's say if you already know that an egg type is I mean, we could also add that in here, I guess. Basically that. You know, add support for getting a single field if you already know the type of something, and also the same for the variants. Yeah, then here we can just do the variant struct. Well, yeah. And this one here would be the field arguments. Fields, and then in there we have, you know, the variant. No, that's an array. That's everything we know. That's a single field. And variant is just type dynamic dot invariant enum, and that is type dynamic dot variant lambda. Yeah, type range. Let's move that a bit further up. Maybe here. Nice. Cool. Oh, I see. Yeah, okay. Let's do something about that. Yeah. Nope. Types. Okay, but this everything type checks now. That's at least something. Let's see if it makes sense. Well, so we are doing internal kind. Y is a weird type. All the others seem fine. All the others actually. That's cool. That is so cool. Internal kind of something. Well, specialize rec. Somewhere in here. Let's print that. So we're doing internal kind of something. doesn't seem right. Okay, so we do have a struct here. Then we specialize the fields. That's going to call this map here. Let's look at the types of the struct fields. Oh, what's going on there? Specializing this struct, and then that gets turned into that. Oh, oh, I see. Ooh. The underscore. Underscores are currently not allowed in types, I believe. See, that's the kind of error that you get when using strings as your, as your data structure. But apart from that, I think this works out fine. Yeah, there was some like consume name or something. Maybe not. Return the kind. I don't know. Down here. Consume name is alphanumeric. Let's actually get the character. Oh. Nice. So we do have a couple of bytes here. A couple of types, I mean. Damn, that's a lot of types. Is that stuck in like an infinite loop or something? Maybe. But there's no Stack Overflow happening, so that's a bit confusing. Interesting. But it does seem somewhat repeating, I think. Yeah. Okay, Stack Overflow. Oh, maybe not. Oh, out of memory, yeah, okay, basically. Fun. I guess. Huh. So the joining takes forever, basically. That's interesting. What kind of types did we? Well, I don't know what kind of types to try to join, but we have this kind of wedge of types, and And this really is kind of repeating. Oh. Well, okay. Let's first of all not print that. Internal. Was it internal kind of? Yeah. That one, let's not do that, but instead in the joining, is that the union? Yeah. Here we are joining types. Let's print stuff. The really, really weird thing is that the stack doesn't seem that deep. We have the main. Sure, that's a couple of joins, but it's not like we're filling up the stack with infinite columns. I mean, maybe each of these is quite wide, so. But still. Weird. Alright, let's print that. Let's say, Oh, I think I know. I don't know, maybe not. Yeah, no, never mind. I was thinking maybe they are not, before they were canonicalized here, and then we checked whether they are in the currently joining map. Maybe they are not canonicalized now, but yeah, now this should be even better. Always canonicalized, basically. So, that's not it. Is that fit on the same line? No, not quite. Let's condense that a tiny bit. All right, so let's print what we are drawing. Oh, that's interesting. We're specializing types. Whoa, what's going on here? Oh, now we are joining all over the place. Okay. Okay, let's see. Not sure about that. So I don't even know where the border between the two types is. Oh, here. And welcome. Boom. Like that. So we are joining, boom, this type. An array of other types of whatever have you, and this other array type. Yeah. Let's kind of see how that started. Now we can't see that, okay. But let's kind of go through a couple of these just to get a feel of what's going on here. Okay, so we are joining, for example, this enum, boom, and this other enum. Both of these should be fully canonicalized. Let's just make that sure first. So this enum has what? Oh, this is like a type. This is the dynamic type. Yeah, it's either an enum with a name, which is a string, and a value, which is again a dynamic type. So pointing up to the original enum, or it's an int, or it's an array, or it's a lambda, which is an actual lambda that takes an array of. Oh, that doesn't seem right. Which takes an array of dynamic types. A lambda that takes an array of structs. Oh, that takes an array of an enum. I see. That then contains, you know, a struct and what have you. Hang on, I think this type is not canonicalized. Let's kind of paste that in some file and just look at it. Okay, so this is a struct that then contains an enum that contains a struct that contains a name and a value. Alright, that seems fine. So it's either an enum or it's an array, or it's a lambda, in which case we actually have a lambda that takes an array of an enum of something that is either a struct, which then contains 1, 2, 3, 4, 5 opening parentheses, and then 1, 2, 3, 4, 5 closing ones. So this again is either a struct or an enum or an array or a lambda or a type or a byte or an enum. So 1, 2, 3, 4. 1. Boom. Like that. Yeah, an array, and this lambda returns, oh look at that, another enum, another dynamic type basically that is also a struct, or an int, or an array, or a lambda, or a type, or a byte, or an enum, or whoa, what the hell? I think I throw more parentheses here. 1, 2, 3, 4, 3, 2, 1, 2, 1 here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Boom. Does that match that? 1, 2, 3, 4, 5. 1, 2, 3. That does seem. Yeah. All right. Okay. So there's kind of an enum. Oh yeah, no. Hate you. I mean, that makes sense, I guess. First of all, let's replace these for simplicity with string. Just to kind of understand the structure here. this does seem correct, you know. Yeah, this is an enum or an int or an array or a lambda or a type or a byte or a struct. All right. So apparently this is not fully canonicalized, I think, because I want this. This one right here has, it's like lambda 3 levels up. It's like 1, 2, 3. Yeah, that's this lambda. Makes sense. That does make sense. But then hang on. I think I get it. Maybe. Let's try to simplify that. Our canonicalization, the way that works is it just, okay, let's make that in a new file. Well, anyways, the way that works is it just tries to bubble up these types. So in this lambda, for example, what I would want is for this to be like, 1, 2, 3 types up, something like that. Something like that. A lambda of dynamic values. Lambda that has an array of dynamic values. Yeah, and that produces another dynamic value, like so. Oh yeah, by the way, these need to be further indented, dedented. All right, that doesn't happen though, so let's see why that's not the case. The way canonicalization works, it just tries to bubble up these recursive types. So I think it should, in theory, kind of see this one and then try to replace the surrounding type, aka this ampersand, with that 3 layers up. And that's like 1, 2, 3. That's not the same type because struct now contains a lambda. Okay, so then it's basically done with that. And then same here, it tries to bubble that up, put the 2 directly in here. And again, not the same type because now this array doesn't contain an array, but it contains a lambda. Fair enough. But now the lambda is here. And this is where I would expect this to work, to kind of bubble up to the parent, aka this enum type, like so. And then it should figure out, oh, that's the same type. Because like 2 levels up is 1, 2. Oh yeah, that's that's the original dynamic type. And same in here. Here's the lambda 3 that should bubble up like so, and that's the same type. So for some reason that doesn't happen. I have no idea why. Let's debug that. Yeah, let's say we don't kind of re-disable that one and only test the canonicalization. Let's say we have some type. Type, what was it, dynamic? Okay, that's the type dynamic. And you can see that the lambda is exactly that, an array of 3 levels up recursive mapping to 2 levels up recursive. Now what if we access dynamic dot, we know that's an enum. What is the type of the lambda then? So we want the variant enum. That should correctly wrap around. Okay, so the enum, hang on, variant enum, yeah, I want the variant lambda. Okay, so the lambda is this. It's a lambda type that takes an array of types. Makes sense. And it returns another type. Makes sense. Now let's say I want to look at the struct of that, at the field arguments. Is it called arguments? I think so. Maybe not. Oh, that's not a struct, so we can't do field. We can do kind, and we know that that's the lambda, and then we can unwrap that, and then we can get the arguments. Like so. Okay, args. Sure. Let's use args. Boom. These are the arguments. So this is quite big, I think. This is an array. Let's dig into that. Type again. But yeah, the point is this is, oops, this is an array of the type. So this is an array of types. But then within these types, the lambda doesn't just store an array of like recursive 3 or something, but instead it contains the type definition again. That's not fully canonicalized. So I think the extend 1 level is not quite correct. Maybe that's the case. What's that called? Like that's the, oh yeah, that's part of the core type logic here. Well, here we have the internal kind, sure, and then here we have navigating into types. Extend recursive types with an extension. So for the lambda, I mean, I guess it kind of makes sense conceptually, the extend 1, what was it, extend 1 level, extend recursive types. This complicates the type. you know, this is the lambda, and now this is this is a more complicated type. We have the dynamic type 2 times in here. Once for the arguments, and then a second time for the return value. I see. But then I think if I just navigate into the arguments, that shouldn't do anything to the content of these, right? Oh, I see. This lambda type is replaced with the entire lambda. You know what? You know what's the simple solution? Just extend that with recursive types. Yeah, sure. But then canonicalize that. Where's that? Kind. Searches on the internal kind and extends that. Extend recursive types should just canonicalize that, I believe. Yeah. Oh, hang on. Doesn't that navigate into types? Well, that's difficult. So tightly interconnected set of functions. Getting the kind of a type which extends it at the bottom and gives you, kind of a new version, new canonicalized types for the individual fields. I don't know. Yeah, I'll have to think about that a bit. Okay, I think I just don't need the canonicalization when checking for equality. The fundamental problem is that navigating into types is supposed to result in canonicalized types. But canonicalization kind of creates these simpler candidates and then checks if they are equivalent to the original type. So canonicalization depends on equivalence checking, and equivalence checking depends on navigating into types. So we have these kind of three-way relationship. Navigating into types depends on canonicalization, which depends on checking if types are equivalent, which depends on navigating into types. Wrapping around dynamic recursive types and so on. So I believe the solution to that is I need to break that cycle up. And canonicalization has to be able to navigate into types. But I don't think they need to be fully canonicalized. They should extend at the bottom, sure. but they don't need to be canonical, I believe. So I want to build some sort of other function, you know, kind, an uncanonicalized kind. Oh, here it's always called like without canonicalizing. That would also be nice. Kind without canonicalizing, like so. And then this type we'll just call, you know, kind without canonicalizing dot canonicalize. That means that there's extend recursive types that doesn't need to take care of canonicalization. Where's that? Here. Yeah, this doesn't need to canonicalize types. And then in the union, oh no, hang on, and the unioning is kind of independent from that, but the canonicalization, equivalency checking, that doesn't need canonicalized types. So yeah, here in this is equivalent. Here we are fine with kind without canonicalizing. Although we shouldn't, you know, we should only replace recursive types that reference the root node, but I think we do that already. Let's see, kind without canonicalizing dot canonicalize. Oh, that's true. Yeah, I think we need to switch on that actually. Yeah, if it's a variable, then we can just return that, I guess. If it's never, we can just return that. Same for byte, and for int, and type, and well, for array, we have an item type, and then we need to do type kind.array of item.canonicalize, like so. Yeah, for the struct we need to canonicalize the fields. So yeah, that's a map to egg types, and then for every field in the struct we need to put that in there. And then return egg type kind struct of those fields. Yeah, something very similar for enums, except this is called enum. Oh, this one as well. And the fields are called variants. Alright. Then next up we have lambdas, I believe. Struct enum lambda, yeah. With arguments and the return value, sure. And that's it. So for a lambda, we result in egg type lambda where the arguments are just canonicalized. Same with the return value. Alright. Oops. Let's try to run that. Oh, that's taking too long. Something fishy is going on there. Okay. Let's maybe check the is equal. And like is what is equivalent, that one. Yeah, I'm just gonna print and then we print A, B. Dang. It's quite a bit of stuff that's going on there. How's that? Like, currently compiling must be crazy long. Let's maybe put those on separate lines, maybe a bit indented. And then let's say for every thing I'm currently comparing, yeah, that's the one. We also print that type. Let's see. Okay, we do have a whole bunch of types there. What? Okay, so is equivalent of this struct and this struct. And we're currently comparing these. And like these are literally the same type, right? And lambda of array of 3 mapping to array of 2 and then a struct of not quite. This part is different. Fair enough. Let's maybe print that. Instead of doing that. So that should give us a clear indication of whether we're just, kind of this infinite loop is outside of the is equivalent thing, or whether that's inside. Oh, I see. This is still printing stuff. Okay, this does check stuff. It makes progress. It's just very, 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 very slow. Why though? How many recursive calls are happening there? Kinda scared to check, you know. Oh, global mutable variables. How I missed you. Calls. Okay, that's not too 20. Oh, hang on. 500 something, 5,000 calls. Like, first of all, 20 calls doesn't seem too bad. Why does it take so long? You know. But then 5,000 in one case here. 2,000. I don't even want to know how many calls those are. You know, some of these are fine, some of these are just outlandish. $5,000 calls, 7,500 calls, 2,500. The trues, they are really, really expensive. The other ones, not so much. $52,000 calls. 32. Okay, yeah. I mean, I get why this is taking long, you know. Let's turn that into a reverse iter first of all, because it's very likely that we kind of, if we traverse deep down into a type and there's a recursive type deep within a type, this would kind of make it easy to see that without getting stuck in the upper parts of the type. Also, let's just have, you know, if A equals B, then we'll just return true. I think that's very fair. Oh, iter ref, ref iter on slice. To slice then, I guess. Same thing, still takes a long time. Sometimes, yeah, 2,000 something calls. that one's really down. Yeah, 43,000. Not as bad as before, 52,000, but still. That's not good. Not good at all. I think we don't. This doesn't have to be a stack, you know. Let's just let's not pop these. You know, let's just propagate that and oh, that is way faster. Nice. That makes sense. That actually makes sense. Like if we have a complicated call, you know, like let's say this one, you know. Well, maybe. No, I think like 14, you know, sure, 29 calls. That's 40, yeah. But it's not that one of these, like, you know, some of these orders of magnitudes bigger than the others. That's the main part I was worried about. All right. Yeah. The thing is, if we have, I can explain this. You know, we have an enum that is either foo or it's bar, and this is like the type. Let's say the type foo, and then it's either A or B, and then it's empty something, you know. And A is what A is, I don't know, array of foo. B is array of foo. Currently, we try to look at is the let's say the second type is this one. Or maybe even, I don't know, something. To check whether these are equivalent, we kind of, you know, assuming we didn't do the string comparison operation, that kind of optimization first, we would compare the individual types. Like this is an enum, this is an enum, those are compatible, and then we would look at the variance in a pairwise manner. So we would look at empty is empty, okay, the payload is an empty struct for this one, for this one as well, like so. Then we would look at this one, and then we would compare array of foo to array of foo. And then for this case, we would also compare array of foo to array of foo. Now, if these are some really complicated types, then we wouldn't take advantage of that over here. So, yeah, these, you know, comparing contains all the types that we are either currently comparing or that we have already compared. Basically, the types that are considered equal, you know. All right. Cool. So let's remove the printing here and this one, and let's just simplify things even further. Let's move this over there. Boom, boom, boom. All right. Well, let's remove the debug logging from here. Oh yeah, also the calls tracking. Oh, that did take quite a long time, I think. Printing this type, sure. Then this type. Let's see. Oh, yeah, that takes some time. Wow, that's not good. That's not good at all. Why is that taking so long? We do the canonicalization. Where do we do that? Yeah, there are lots of, you know, recursive types in there, that's for sure, but still. Yeah, that is something. Let's not print that maybe, and not that one. And just count how many times we do this. How many times do we bubble up types? Hmm, 16 types. Doesn't seem too bad, I would say. We're also canonicalizing lots of types. Just realizing that. Oh, these are like built-in types that we use. Okay, that makes sense. Yeah, this is basically the main function. Alright, and then we have this type that we canonicalize. Then int for some reason. Okay. Then this array, and then this lambda. Not sure about that one. Okay, let's nevertheless let's simplify that. These types are definitely not the same, so bubbling up some recursion doesn't even do anything. I'm wondering, that does make sense. And like, let's say we have some type in the, let's say down here, we figured out that we can't optimize anything in there, but here we can bubble this up, for example, and replace that entire thing. Then it wouldn't make sense in the next situation to start retrying to bubble up these, but instead we should continue over here. Yeah. Not sure. I'm not sure what to do here. But bubbling these things up should be quite cheap, I think. Yeah, here there are 5 recursions, but this is already canonicalized, so makes sense. So that shouldn't take long. Why does it take long? mean, that is equivalent is probably the culprit there. Yeah, let's print that again. How many times we're calling that? Oh, hang on, we can just check how many items there are on this list. Yeah, that's not super fast. Like most of the time we are after the question mark, the cursor. So the majority of time we really spent in that is equivalent function. That kind of sucks. Okay. Think. So this is calling what extent recursive types. And that kind of kind of recreates, like basically creates a lot of maps and so on. I see. Even though we don't really use them. Mm-hmm. I believe that extend recursive types is the culprit. Is equivalent calls kind without canonicalizing. Let's check that. So let's say kind does that, and then down here we just say, yeah, we return the kind, and we print done. And up here we just print that. Yeah, a lot of time we're just waiting for the kind. Especially that extend is probably wait, multiple times. Yeah, you're basically spending most of the time extending the types, which makes sense. Let's refactor that. Let's say that we want to extend recursive types, but we don't do that by kind of traversing the tree and stuff like that, which is the expensive part. And instead we're building a new type, and we're just iterating over the original one, keeping track of the nesting. And basically we just check, do we see an opening brace, opening parenthesis, then we increment the nesting. Do we see a closing one, then we decrement the nesting. Then we also check if we see a recursive type. Then we need to pass the nesting. So then we do consume name of type substring cursor plus 1. we increment the cursor so that it points to the number. Then we take the substring from that cursor to the end of the string and consume the numbers there. We pass that into a level. Let's do that, and let's say, yeah, we pass that into a level, and if the level is equal to the nesting, nesting -1 is a recursive type that references the root. Replace it. Then we replace that with the extension, and we move the cursor to the current cursor +1 plus the length of that thing. That leads us to the closing parenthesis. And we still have the parentheses, so we don't care about the extension. Yeah, something like that, yeah. And that would basically, and we don't have to do this. We don't have to actually like traverse the entire tree and filter out the the fields, put them in a map, all that. We're just iterating over the original string, and we're appending the characters to a new string. Except when we meet this kind of recursive thing, then we try to pass that as a number, and then work with that directly. Okay, this call doesn't work without first with an egg type. Oh, I see. I should rename that to string, maybe, the field. That's a bit more descriptive, I believe. All right. Yeah, at some point we need to get done. Yeah, fair enough. Oh, not quite. Bubble up recursion. What's going on there? Get ref. Some character. I mean, yeah, that's certainly something. Okay, hang on. We are canonicalizing something. We are canonicalizing this one. recursions is 1. Hang on, canonicalizing, is that called with an unfinished, a not self-contained type? Probably. Yeah, that's bad. Oh, from where's that called? From kind on egg type. Okay, yeah, we're getting the kind of this one. Then here we are extending that one. Oh, I think the extension is not working correctly. Which makes sense, we've just changed that. Then we have the extended type. Oh, no. No, 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 no. Hang on. Canonicalizing this one, that's invalid, yeah. Here we're canonicalizing that one. That's not reasonable, because this one is not even valid. There's value 3, but it's only 1, 2, 3. 3 doesn't exist. It's not self-contained. Same here. And here already. Let's check that. So we're canonicalizing this type. The lambda type, is that correct? 1, 2, 3. Yeah. This one 2 up, so that would be 1, 2. What's correct? Okay. Then here we are. We have this enum. And then we want to get the kind of that enum. That makes sense. And so we are extending the one. Oh yeah, this is not extended. Why not? We have 1, 2, 3 opening parentheses and then type. I think we had some sort of +1 in there. We don't need that. Yeah, I think this can be that, kind of directly that. Oops. Oh. That seems fine. Nice. But fast? Reasonably fast? Well, depends. Const target struct. Would be really good to have some sort of profiler for Martinez. Well, yeah, let's just remove a lot of the printing and see if it's a bit more obvious where things don't work out perfectly. Yeah, all of this has become much simpler. Just walking over a string. And like this is so much shorter. That's honestly surprising. Yo, that's quite a bit of output. I mean, you know, it is faster. I think. Yeah. That's quite fast, I think. Yeah, much faster than before, at least. No. All right. So, where do we go from here? I guess let's put that in here again. and just see what happens. Oh no. Well, it claims that it returns an enum. Which is either empty or more. True. But then actually it returns enum that is either more and that is always more. I see. With an item, which is a T, and then the rest, which is an enum that is either empty or more and is recursive. Oh, that seems wrong. Yeah. We create these root types. And what did that do before? I think before all that we the recursive extend recursive types that one had an extension, yeah, they called extend recursive types. But then when there was a recursive type, it would actually replace that root one with the level. So this is the extension, replace root. Okay. That is certainly something. Okay, that compiled. It took a long, excruciatingly long amount of time. Like one thing we should do is that will kind of alleviate a lot of the differences there. What's going on there? This is just to return some type. Faster, much faster. Still slow, but think unioning doesn't actually take that long, I believe. Looks like something else is taking a long time. I can possibly there's a print joining nowhere. Okay, I think I'll just remove that, so that's fine. But yeah, unioning this and this, and then in here, after doing that, we can just do done, and then we'll see whether we spend the majority of time in that. Yeah, no. Spending the time somewhere else. My fear is that it's in canonicalization. Yeah. Yeah. Let's also print the resulting type. You know. Just to get a feeling of, are these different types? Is this canonicalizing the same type over and over again? Is this what's going on here? You know. Okay, there was some stuff going on. Then all right. I mean, yeah, we have a lot of dynamic types, I guess. That's what that is. Yeah. that bunch of times, bunch of bytes. I believe it's kind of you know, we have a type, and we have that same type again, and again and again and again. I think I'm gonna add a cache there, a cache of canonicalized types. Basically just a set of egg types. And then I could check, is that, you know, like that, I believe, empty. Canonicalized types cache dot contains the type. Then we'll just return the type because it's already canonicalized. And down here we do is this a bit of, you know, oh, things are slow, so we're just caching stuff instead of actually doing, like, making them faster. That kind of, yeah, that is kind of what we're doing, but I think deciding of some complicated types like these, you know, if they are canonicalized, that is just a difficult task. But we don't have that many types around and, like, floating around in the program. So I think it just makes sense to cache that. That is not like unclean or something. It's just, it's useful. I do want to rename that field to string. Like type.string would at least make a bit of sense. Yeah. I'll return that type, obviously. Still taking some time, but at least it's a bit faster, you know. Hang on. We don't. This is not cached. Canonicalized types cache. If that contains the type, then we just return the type. Wait, where did we put that into the cache? Here, and extend recursive types. Oh no. That's exactly the wrong kind of... No. We want to do that down here. Let's see. Yeah, at least, you know, now the types are strings, they are really... It's quite a lot. That was more than before, wasn't it? What the hell? all of these unique types. Are you kidding me? Like this type is the same as this one, isn't it? Let's see, array of 1, yeah, and byte is an empty struct. And then this one, yeah, that's just... That's the same one as this, right? Array of 1, an empty thing here, then an array name, which is an array of bytes, and a type, which is 3, and a lambda with arguments array 3 and return type 2, never recursive int, struct with name UTF-8 bytes, array of byte and type 3, and then type. Yeah, that's the same type. And then we bubble them up 10 times down there as well. Canonicalizing. What? I don't get that. How is that working? Are global variables not mutable? I mean, that would be a possibility, you know. I just thought they were mutable. Let's try that out. Still a lot of stuff that's happening there. No, that's not cached. Not cached at all. Yeah, no. I mean, at least, you know, these are the same type. Why is the same type canonicalized 2 times? Let's factor it out in there. And then maybe there, sure. And then here we can just do return the type. That actually just, and then we do type.canonicalize uncached. Put that in the cache and we return it. How's that not working? Hang on, we have equality checking and hashing for types. Checking if 2 types are equal just compares the strings. That should work. Hashing a type just hashes the string. That should also work. Let's maybe print the hash set up in here. Or at least just say cache has some entries. I think that's like a map. Internally it just has a map from type tool nothing, which is pretty elegant, I think. Okay, so there are entries coming in, but they are just not considered equal, apparently. Yeah, that cache doesn't have any hit rate. That's unfortunate. this is the same type. Oh, hang on. Cache has 219 entries. Canonicalizing done. Still 219 entries. So that was in there before. And then it gets canonicalized again. Okay, so the hashing and equal works. Let's look at contains. That is the Martinez standard lib set. Yeah, contains some T. That just checks if the map contains that key. Seems reasonable. How does the map work? Map. Yeah, does it get maybe of the key, if that is some. Yeah, and that should work, because I'm using that all over the place. How is... I mean... Like I'm basically debugging the language or something here. I don't feel like I'm, you know, fundamental assumptions. This should be false. Or at least if, you know, afterwards it checks. This is... Yeah. Okay. I mean, apparently, sometimes we hit that cache. Because here we're always printing that without any canonicalization being made. Yeah. What the hell? Oh. Oh, I see. We are printing not the type that we get, but the canonicalized type. I see. Do we maybe want a map from canonicalized? A map from egg type to egg type. SA. No. It does take a long time still. I don't like that. Yeah, okay, but only the big ones take a long time, like these ones, you know. Which makes sense. It does make sense, I guess. Why does it take so long? Like these take a long time. You're bubbling up 19 times. Of course that takes up some time. Oh, this one, you know. I think we can do better here. Basically, I want to have a cursor at which type we are currently working on bubbling that up. Starts at 0, and then if I is larger than num recursions, type of count recursions, then you break larger or equal. store the baseline. We bubble up the recursion. Also increment the bubble up counter. And then if that is still self-contained, they have to be equivalent. Yeah, I think we can if we have a big type and at some point we bubble something up, that may mean that the type now has less recursions. Like if there's, a struct with some recursion that we've already tried, and then our recursion. Well, our recursion kind of consumed that. And then we move the cursor a bit, kind of back to a recursive type that could have been affected by this change. Mm-hmm. It does seem faster, I believe. Not entirely sure, but a bit faster. That's good. Plus we can maybe check that in here. Try that. Whoa, what's going on there? Oops, sorry. Oh, I see, because we don't necessarily print the end. I think that's actually slower than before. I think this kind of makes sense. Yeah, let's go with this one. Actually, not sure. 4.8 seconds, and with that in here, 4.8 or 3.8. I'm not sure exactly about that. Yeah, I can let that cache. Yeah, no. That is kind of unsatisfying. Is it just that we have to like canonicalize a bunch of types, and that's what makes this relatively slow? Or is there something deeper to that? I want to optimize that even further. Like, what's the super slow one? Let's do like a micro benchmark on that, and I think I can do like a timer or something. Is that a thing? Let's see. Time. There's instant, there's start timer, and then read iteration. Let's do that. Start timer, and then down here we can do couple microseconds, I mean, sure. Milliseconds, that's something. You know what, let's only print that if the time is larger than 100 milliseconds or something. I think you could do that in milliseconds. Yeah, let's print the original type maybe. Oh, that's not on float, I see. Sure. You can't compare you can't compare durations apparently, which is unfortunate. Okay, so I'll just do milliseconds in seconds. Something like that, maybe. Seems to compile at least. Okay, so these are only the slow types. Dang, like 200 something. Yo, that's by far the most egregious one. This type. I mean, yeah, I wouldn't want to canonicalize that. I mean, it makes sense. I guess it makes sense. Like in the dynamic function, for example, you're just constructing an enum, you know, and where was that? The any function, I think. Yeah. Here, you want to create a dynamic, but you're just, you know, the type of this is byte of a byte. This is an int with an int, this is a type with a type, this is an array of dynamic values. Yeah, an array contains an array of dynamic values. Boom. Yeah, that's quite a bit. Let's kind of only recreate that and like in here. Let's say we have a type enum where, what is it, array is an array of dynamic and int is an int and byte is a byte. I'm just going through this. We have byte, we have int, we have type. We have an array with a struct. Which is an array of fields with a name and a value, and we have an enum which is just struct, and then we have a lambda that's a lambda with the argument being an array of dynamic ones and the return type being dynamic. Just constructing that should require some canonicalization stuff. Yeah, 288 milliseconds. 22 times, that's exactly what we got before. Like, obviously the time doesn't match exactly, but around the same value. Yeah, I want to improve that. That's add some debug prints first of all. Also print an indented version of this type. That's probably fun. Oh, that's the type. That is the type that we are canonicalizing. Whoa. Okay, that is something. I have to admit, yeah, that's Oh man. So how does that work? Let's print the beta versions in here. As we simplify that type. Alright, let's see. We start off with this type. Yeah. So this is an array with, the indentation is weird, but with a name and with a value. You can see the value is another enum. First we try to bubble up this one. And no, we don't. How is that version an improvement? This one has Oh, I think this one's better. Yeah, we have array of this one instead of array that contains an entire enum. I see. And it makes sense that we start with that because we go through that alphabetically. A like array. Alright. I guess that makes sense. Then we and that's already quite a bit shorter. Then we find another even better version where we simplify enums to store the value directly in line instead of like this. Alright, and then we do the same for, let's guess, for lambdas, like that. And then for the lambda return type, and then for structs. Alright. From high level, this seems reasonable, I would say. Yeah, is there something we could improve? I mean, first up, the printing of arrays. that's a no-brainer. So well, that's it. Yeah, for an array, I think we don't need to print the indentation here. This already prints its own indentation. Oh, and we've already formatted that as a single line. Oh, I see, so we don't even need this special casing here. Also nice. Yeah. Yeah, lambdas are still weird. So I guess I would have to let's not print these, but let's instead try, you know, and what's taking so long. For these individual checks, is that the bubbling up? Is that the checking for equivalency? Is that, you know, this one? Who knows? Okay, and what I want to do that in a loop, I think. That might mean that I have to disable the cache, which would be fine. You can see that the cursor is basically bubble and check is always there, but the done part takes a long time. So the checking is what makes this expensive. All right. Fair enough. This is canonicalizing. And we do and then done in 200 something. Let's also print the I maybe. this could return how many types before that, how many recursive types before that were removed. But really I want to get into the check. I want to see what about this is so expensive. Some logging. And then some bookkeeping. Okay, the equality checking is most of the work. Which I guess makes sense, because equality checking in and of itself is also quite expensive. So, so in here, let's maybe at the end, like, let's just print the cache length. How many types do we check for equality? Oh wait, was that 100 there? Okay, not 100 at least. Well, that's 17, 35, yeah. This is weird profiling, by the way. You know, logging stuff and seeing what the log output is, where it's kind of stable, but useful. Okay, so 35 is the biggest one, and in general, like, equality checking takes a long time. This equivalent, what does it do? It checks if two types, if they are actually the same, then we take a shortcut. Okay, that makes sense. And let's not call that comparing, but equal or something. All right. let's just print a dot. Then we'll kind of see how the dots grow there. Dang. And some of these do quite a bit of work. Checking 35 types. That is quite the number. Ooh, ooh. Okay, I have an idea for a new strategy. Rather than iterating into this, like kind without canonicalizing, and you're kind of eagerly constructing a new type with a new string with stuff. What if instead of that we would keep track of a stack of types that we are currently kind of iterating into, and then whenever we find a recursive, like we don't extend the types, we just do internal kind. Yeah. We don't extend recursive types at the bottom, and whenever we meet a recursive type, we can kind of look up in this recursive in the stack which type that actually corresponds to. And that should work. That should work. That's quite cool. Although it does make things weird with this list, because now like these types, they have to be self-contained for this to work. Do they? think so. No, yeah. I mean, alternatively, another option would be to simplify the kind without canonicalizing. Like, I was thinking, what if instead of this root thing and then extending recursive types with that, what if we just put the entire type in there again? But that might lead to deeper types, which is not really what we want. Well, let's print the types first. Let's say that in here, yeah, we actually print the types that are equal, that we kind of considered. So that's going to print a lot of stuff, obviously. What's going on there? We have is equivalent. Oh, I see. Yeah, no, that was just some out loud thinking, not actually. Yeah, I'm especially interested about the like 35 something. Oh yeah, it should still print the cache size. $17. 14. I mean, what have we really done here? We have the array. Oh, there's a space in between. Obviously. Oh, I see that. are these types equivalent? Array being an array that is recursive 2, a byte being a byte, and enum being name and value. Then an int, a lambda, and then a struct with an array of name and a value, which is an array of 2, byte, enum of 2, an int, a lambda. Oh, that differs. And a struct and type. Okay, so in the first type, lambda is this thing with an array of type 3 levels up, returns whatever is 2 levels up. And here we tried replacing that with this one. That's not the same. So that should result in false at some point. Yeah, nope. Not the same. But in order to check that, we then extended the types, I think. And we looked at the inner types. All right. The inner types of the what? I see. In order for those types to be the same, the enum types have to be the same. And in the first case, the value of the enum is this one, because this has been extended with the same name, but the value referenced the surrounding one, so we've kind of inserted that in here. I guess, yeah. While on the right side, the enum is something different. You know, with a different lambda implementation. Instead of this one, we have this one. And then this one contains an array. So we need to make sure that these are the same. You know, an array of something with a lambda inside, and another array with this lambda inside. Hang on. Yeah, okay, I guess. And that kind of goes on and on and on. Oh, damn. This type well, 2 types, but still. That's quite the big type. Yeah, that kind of gets trimmed down, and then we have this one. Okay, I think we can do like a small, you know, kind of sanity check maybe. Like if we replace a recursive type. I don't know. I might think about this more. I'll just take a break. Okay, so let's first rename the type into string. You know, like this inner field here. That's really just a string, because I mean type.type that reads kind of weird. Type.string tells you, oh yeah, actually just taking the string of that type. All right, yeah, we have that. Then type enum without canonicalizing. Yeah, not sure what that one. Let's yeah, that makes sense. That also makes sense. This one, nope. Let's take the string, and in here let's take parent closing as type.string. Yeah, that's fine. Now then, another place is when constructing types. Yeah, exactly. We have a lot of these places where we have egg type. I think that's the better term to search for. Oh damn. Yeah. Basically here we just want to have strings. Like these should be renamed like that. And then we can just look for other ones here. Oh, this one is that. That doesn't quite work. But we can do that. String equals that, and then in here, that is fine, 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 fine. All right. Now, what I wanted to actually do is I had an idea on, hang on, first let's compile that, see if that works. Then I had an idea on how to make equality checking way more efficient. Yeah, this is taking most of the time, the equality checking. Yeah, okay, that's expected. Okay. Basically, where's that function? Is equivalent, yeah. When we are doing this, we first of all, this is a recursive function, and we are checking whether two types are equivalent by getting the kind without canonicalizing, but still we are kind of wrapping the type around. We are building a new type, kind of traversing down the type at the top and then breaking it up at the bottom. And what if we don't do that at all? What if we just keep these two types as strings? And then we just have two indices through these strings. Yeah, so that's basically what I wanted to do. You know, just rather than this, we'll just have a string and a string, and a cursor, which is an int, and b cursor, which is an int. And then the equality function here just needs to store tuples of integers, tuples of cursors. That makes sense, right? Yeah. That does mean that we can't do this like trivial check in here. That only works in here. If their string is actually the same, but still. Yeah, here we create a list of equal cursors, and then we do is equivalent of that, of those two type strings. Let's say A type, B type. And the cursors like so. All right, yeah. Is equivalent. Alrighto. And then in here we iterate over them and see if this already contains the cursors. Otherwise we push a tuple of the cursors. And then we do the is equivalent logic for the A type, and B type to A cursor, and the B cursor, and the equal types considered equal. And then here again with an A type, which is actually just a string, and a B type, which is just a string. Then an A cursor, which is an int, and a B cursor, which is another int. All right. Yeah, so then what we can do in here is we don't do any of that. Instead, we get the type at the given position. And that does mean that we need to handle recursive types, you know? But basically we can just check like a let's call these not a string, a type and b type, but a string, maybe, because this is like the kind of the entire, I don't know, universe, the entire thing there. Yeah, and then what we do is we do, you know, a type is a string dot without the first a cursor characters. That gives us a cursor that should point to an opening parentheses, and then we should be able to do consume type. That returns to us the, you know, basically a tuple with the first part, the type in parentheses, and then the rest of the string. We only need the first part, that's a string. And then we can do internal kind to parse that into, you know, like a recursive type. Is that recursive? Is that an enum or something? But that type is no longer like self-contained, you know. Let's actually call those kind, I guess. And that is just b string without first b cursor dot consume type dot a, because that's just the tuple index. Yeah, and then we can check, you know, if a if that is recursive. And then we actually just, you know, return what is equivalent of a string b string to do b cursor and equal, and here kind of need to follow, kind of bubble up, you know, the string. The kind of the recursion anchor or the target or something, you know, and let's just start at the a cursor -1. Yeah, we also need to contain a nest, like maintaining a nesting here, which is initially 0, and then basically if the let's get the character from the string first, like a string dot chars dot get target yeah, that should work. That has to work because these types are self-contained, the a string and b string strings. And then we just, what do we do? We have the character, yeah, if the character is that, then the nesting is decremented. Yeah. If the character is that, then we're going backwards. So we are moving into a parenthesis. So nesting is nesting +1. Yeah. And I think we also want to check if the nesting equals minus the target. Oh, I see. Yeah, there is no unary minus. Then we want to break, I think. Let's see. Let's imagine we have some type foo. Like that's not type. No. Like a is, I don't know, int, and b is say this is actually enum, and b is the kind of recursive one layer up. Instead of actually like traversing down into the type and building new strings and wrapping that around and concatenating stuff and whatnot, we just maintain a cursor. We maintain a cursor that points to where we are currently at. And then when we are here and we want to inspect that type and we see that's actually a recursive type, then we want to go one layer up. So we start at target is a cursor, this one, -1, so this character. And then we go backwards. The nesting is 0, but the target is 1. So we boom, move this. Nesting is now 1, and the target is 1. Boom, now nesting is 0, and the target is 1. And then boom, nesting is -1, and the target is 1. So then here we just break. Otherwise we say the target is the target -1. Let's call it cursor, I guess. Yeah, and then here instead of the a cursor, we just use the kind of newly calculated cursor. That's pretty cool. So that instead of building new types, building new strings, whatever, we just have 2 integers that rapidly move through those buffers. And types don't even get bigger, like what happened here. Here you have some type, and then as you extend it at the bottom, that may actually get larger here. That's kind of scary because that may not even terminate at some point. I'm not sure, but I'm sure this is not like a perfect logic there. There were some errors in there, so yeah, this is at least bounded. If you have a small type in the beginning, then like there's only a limited number of cursor positions you can have. So at some point this will terminate, definitely. Alright, if the b kind is recursive, then we just do that same thing for the b type. And then this will be the a cursor and then b. Alright. And then here we actually do stuff. So if a is a variable, then b has to be a variable, or we return false, and the names have to be the same. That makes sense. Never byte int type array, wonderful, is equivalent of oh, I see. Yeah, this is not quite. We do want to get the kind of the cursor positions of those. Also in like enum and struct fields. This is already too high level for us. Well, yeah. Okay, so let's not do this then, and only keep the type. Yeah, that makes sense, doesn't it? Oh. Okay, I do have a cursed version of that. That might work. Oh man. So this internal kind always returns a substring. And maybe you see where this is going. We can what we can do is we check is equivalent of the A cursor, sorry, A string and B string, and then the A item, which is a pointer, which is a substring. We can take the pointer of the string subtract from that the that is hacky. That is so hacky. Hang on, the A item. A item dot data minus a string dot data. Yeah, that's the offset of this substring in the original string. Oh, the hackiness. The hackiness. Man. Yeah. I guess that's fine. Like, also, we could... Like, even this is kind of too much. Like, we don't even need a hash map of fields or something, you know? We don't need that. Don't take strings and then hash them and put them in a map and something. We are fine with strings that we just immediately hash, I think. Yeah, so the internal one was that. Internal find, how does that work? Yeah, it doesn't really have a cursor, that makes sense, I guess. Oh yeah, then it cuts the parentheses. I see. I mean, that is kind of dense code, you know. Meh. That's fine for now. Yeah, this is okay. And then in here we do B has to be a struct as well. The sizes have to match. We get the types. And then in here we can do A string, B string, and A type, which is an egg type. Is that an egg type? Oh, I see. So we really want that. Or we just return false. Alright. And then same thing here for the variants, we just get the variant and then we do basically that. Except they're called arg. The arg and the arg. For lambdas, we check that these are equivalent. Yeah, and here we can do both.a and both.b, .string, .something. Amazing. And for the return value, very similarly, the a string and then the a lambda return type .string .data and b lambda return type .string .data. We'll just return that. Clean. All right. I'm very curious what happens. Internal kind on a string doesn't exist. That makes sense, I believe. Let's maybe call that type. And then a kind is a type dot internal kind, and that. Nice. And you can also immediately do that. Sure. All right. So down here, that is unreachable because we've checked for that before. B kind dot variable. Ooh. Yeah, that's exactly what we want to do. Well, let's convert those addresses to ints. I mean, there's a quite unique pattern, I hope. Without the last amount is too big. Okay. Let's see, internal kind. That does not seem right. I mean, that's cool. That is quite cool. Nice. 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 Now what's going on there? Internal kind of 3. What's going on there? R. Where's the 3? It's here. Then we're like, here's also a 3. Well, no idea where that R is coming from. Oh, let's maybe print the cursors just to make sure that they are something same. So A is 0, B is 0, and then there is 7. That's quite cool, because both of these are arrays. And then we have 1, 2, 3, 4, 5, 6, 7 bytes. This type right here is then compared. That's cool. Then they're like 100, 200, they're getting bigger and bigger. Okay. How long is this? Is this 200 characters? I have no idea. Maybe it is. 226. Yeah. Alright. But this is interesting. So now, like, this makes sense. You know, we kind of inspect this inner type. And then in here, things are a bit more interesting. Let's say we also print let's maybe say when we are checking types for equality, we also print them. And when we say internal kind of type, let's not do that. Yeah, it's equivalent. And then both types, please. Let's see. Ooh. So, is equivalent to this type and this other type. We start with both cursors at 0, this, aka this type, and this other type. And then we continue to 7. That would be this type and this other type. That's quite cool. Then here, first we do like what, 154. No idea where that is, but actually, you know what, let's put that into a file. Let's go ahead and select 154. Here. The struct. Sure. Here's at 154. In B it's at 146 because here there's something got simplified. Yeah, the array here got simplified. Okay, fair enough. So then we are comparing the array the struct contents probably. So rather than this type, we are now comparing this type and this type. Also makes sense. And to do that, well, we have to compare the inner types to the UTF-8 bytes and what this other thing, and then we have to compare these, then we have to compare these. Fine. Then we're comparing 208. Where's that? Where's the array end first? At 200. Ah, look at that, 208. We are still in the struct. We are still in this array, but now we're looking at the value. And this value is 3. This value is also 3. So, in the A variant, we are jumping to the type that is 3 levels up. That should be, first of all, 1 level up would be this struct, 2 levels up would be this array, and 3 levels up would be this enum. So A should be 7 in this case, like that one. But that doesn't happen for some reason. I'm honestly not sure why not. Okay, so we do have a recursive type. And then we we look for the matching closing brace. That should be this one, in theory. Let's debug print some of this. We're looking for parentheses. Looking for, oh, hang on. Minus, oh, no. I was wondering, oh, this is a recursive type, but we don't even use the level of that. We're comparing that with the cursor, not the level. Well, that's kind of cursed. Oh, no. That was unintentional. Okay. Yeah, that makes sense. Whoa. That is stuff. Alright. A lot of stuff. Let's clear this and run that again and kind of jump to the beginning. Assuming we can jump there. Can't. Dang. All right. That looks fine, I would say. Yeah, and we can no longer early abort that. You kind of only look at this, kind of if we see this, then immediately notice that this is the same as this other type. Kind of this early abort of comparing types that we had here at the beginning, because these types may have the same string, but because they are not self-contained, because they still contain recursive types, they may refer to outer types that are not the same. Okay, but let's maybe can we remove these, and also don't print these or this. Oh, that's something. Is it? Oh, hang on, did we? No, that's still not there, okay. Yeah, let's maybe comment out more of the printing, I guess. Like, we do check a bunch more types now, but it's really cheap to check that, so I like that. I like that a lot. Yeah, let's remove some of the printing. Oh, what did I do? I see. Yeah. Yeah, I'll maybe print some of that, sure. Yo, that's cool. Still taking some time, right? Oh, but I don't have I don't have caching now. Oh, I thought this was with caching. Okay, I think that's... I don't know what part of that was the egg, what was, what was what. Oh, yeah, we don't do anything yet. Right. Oh, and we do that 10 times. I see. Okay, then it's definitely faster than before. That's cool. Still taking some time, but I guess better, maybe. Yeah, egg to yogurt, true. Yeah, let's first just try to convert it to yogurt. And that's gonna be just adjusting the compiler pipeline. Egg to yogurt, mod, and then here we can compile the egg type to a yogurt type. Right. So what about recursive types here? Okay, they work. So we just need the internal kind of the type. If that's a variable and something happens. If that's a byte, then we'll just do yogurt type dot byte. If that's an int, yogurt type int. That's a never, yogurt type never. If that's a type, yogurt type type. If that's an array of some item, then yogurt type this one. Array of the compiled item. Alright. Cool. And the only difference is that yogurt types have closures as well, I think. Yeah, egg type is not an enum. You can only switch on enums. Putting to Presto. Why does it have to do anything with egg types? Oh, I see that kind of weird backwards compilation thingy. Mm-hmm. Yeah, the code should get much easier. Yeah, because we don't have to do that, or that, or that, or that. We can just say start compiling. Boom. Yeah, I guess let's go through this from top to bottom. And yeah, we don't need to canonicalize any types. We just compile them. Okay, we'll switch on the kind, which automatically extends that. Yeah, that's not a thing. Instead, we just have byte. Yeah, that's not a thing. That is elegant. very true. That gets so much simpler. All these defensive checks. Now that is rock solid. Types automatically expand as it traverses down into them. No need for checks. Or extend one level or something like that. He never has handled up there. That makes sense. No need to canonicalize. Interesting. Interesting. Oh, and I have an idea why. Because types not always have parentheses around them. Yes. All right. That worked. Pretty cool. So let's optimize the yogurt and run the pudding and whatnot. Run the rest of the compiler. Just see if that works. No. Pudding to pesto. Okay, let's gonna backtrack on that. Oh no. Well, no. I'm pudding to pesto. Before that also took some time. So I'm fine with committing that. Plus now types are canonicalized everywhere, and that's for sure. And I feel like the type handling got a lot more robust than before. Sure, we can still optimize performance, but like a major part of that is just nice. All right. Very cool. Something is still running here. Oh yeah, the yogurt. Makes sense. Very, very, very nice. Yeah, let's also look at the other type stuff that was still remaining here. See if that needs some cleaning up. The builder, I don't know about that one. Seems fine to me. Collect vars. Can be more efficient for sure, just iterating over the string, but not too bad, I guess. Nice. All right, let's go with that. recursive types are missing here. Okay, presenting the problem. How do we present this type? And then one attempt, another attempt. realizing this decision is kind of independent of that one. Whether to use pointers or ints, that's a separate decision from using, that's kind of the preliminary decision, and then you can go on to the decision of enums or something else. And that's also how that historically happened. So, Mm-hmm. I think that's a reasonable explanation. And this is the kind of, I don't usually write a lot of comments in my code, but this is the kind of part where you really want a comment, where you want an explanation of why things are the way they are. And I call that evolved historically and stuff like that. Nice. Nice. All right. Yeah, I guess that's it for this video and for today. Yeah, I don't even know what to do next, but see you in the next video.